In this unit, we're going to be looking at the gradient function. To follow along with the whole unit, go to parkermaths.com/Y1 Diff. We're going to start with a straight line, which has equation y equals mx plus c. We can think of the gradient of a straight line as how steep that line is. And in the equation, the value of m tells us the gradient. To calculate the gradient, we need to compare how far it goes across with how far it goes up or down. We can think of the gradient as for every unit we move in the x direction, how many units do we move in the y direction? And we can calculate the gradient using the formula gradient equals the change in y divided by a change in x. Now, when we're thinking about the gradient of a straight line, it's convenient that the gradient is the same at all points. And so it doesn't matter at which point we consider the change in y and change in x, we get the same value for the gradient at any point. Going back to the equation, we also have a plus c in there. That simply tells us where it crosses the y-axis. But what happens if we don't have a straight line? How could we define the gradient of a curve? Suppose we have the curve shown on the screen. This is a cubic curve, but for the purposes of what we're going to do, we don't need to worry about what the actual equation of the curve is. First of all, we need to define what we mean by the gradient of this curve. Because unlike a straight line, the gradient can't take a single value because the curve has different steepness at different points. So let's start off by considering a single point on the curve. And let's suppose this point has x coordinate of a. To see how steep the curve is at this point, we could draw a tangent to the curve. And as the tangent by definition only touches the curve at a single point, it must therefore at that point have the same steepness as the curve. And so we can define the gradient of a curve at any particular point as the gradient of the tangent to the curve at that point. And that means as our point moves, the gradient of the tangent changes, and therefore the gradient of the curve also changes. Let's explore with this curve how the gradient changes over the course of the curve. So over on the left, the curve has a positive gradient. As we move to the right, we can see the gradient getting less steep until it gets to 0. Then the gradient becomes negative, and the curve proceeds to the right. And then again, it starts to approach 0. And then finally, it ends up positive again. Now that we have a definition for the gradient of a curve at a particular point, we can think more generally. We can define the gradient function as a function which represents the gradient at all points on that curve. And the gradient function, also known as the derivative of a curve, can be written in a few different ways. The two that we meet on the A-level course are dy dx and f dash of x, sometimes called f prime x. And the focus of this unit will be to learn more about the gradient function and how it is calculated. And we call the process of finding the gradient function from the original curve differentiation. To end this video, I'd just like to take a quick look at the notation that we might use. Knowing these historical details isn't something you'll need for your exam, but nevertheless you might find it interesting. So when we use dy by dx, we are using something called Leibniz's notation, which was developed by Gottfried Leibniz. At other points in the course, you'll see us using f-x, which is Lagrange's notation, named after Joseph Louis Lagrange. And so you don't need to remember those facts, but if you hear Leibniz's notation or Lagrange's notation referred to, that's what it means.